So if we know the area of the cross sections, if we were to slice it, so you guys know what a cross section is?
Yes.
So like if I have a cylinder and I slice that cylinder perpendicular to its axis, then the cross section is going to be what? It's going to be a circle, right? If I take a rectangular prism and I slice it and look at a cross section of it, it's going to be a rectangle. At least if I look at cross sections perpendicular to its axis or its length. So those are actually examples of very simple solids where the cross sections are always the same. We have other solids where, depending on where we are, the cross section is going to look a little bit different, like this one. Or if we have like a pyramid. If we took say a square pyramid, for example, the pyramids in Egypt, and we looked at the cross section horizontally, if we cut them horizontally, each one of those cross sections is going to be what shape? If we cut it parallel to the ground, it's going to be a square, right? The difference between that and a square prism, though, is that the squares are going to be different sizes. Okay, at the very top, the square is really not going to have any size. At the very bottom, it's going to be really big, and everywhere in between, it's going to be somewhere in between. So in that case, if we knew what the area of any particular cross-section was, in terms of how high it was off the ground, we could find the volume of that pyramid by using an integral. Now, this is a good example of what we just talked about, using geometry to help us with integrals. That's actually something we know a formula for, so we could use geometry to do that also. Okay, so this is a formula. I want you to just write it down real quick. You don't need to write down the conditional part here, or the hypothesis part of this theorem. I want you to just write this down. The volume of anything is going to be the integral of the area of the cross-section. So this A here is the area of the cross-section. Now this area depends on x. So if we're talking about, say, a pyramid, a square pyramid, x might be the height from the ground. So then the area function here would be the area of the cross-section depending on how high we are from the ground. Does that kind of make sense? So we're going to look at one example here where we have square cross-sections. And we're going to use this square pyramid example. So we want to find the volume of a square pyramid with a height of 3 meters and a base side length of 3 meters using an integral. So we're not going to use a geometric formula, but we're going to use an integral. To start this problem, what I'm going to do is I'm going to try to visualize a cross-section. So if I were to cut this pyramid in one place here, I would get a cross-section that looks like this. How would I find the area of that cross-section? What did you say? Formula. What's the formula for the area of a square?
The integral.
No, the area of a square. Just the area of the cross-section. The area is going to be side squared, right? Now, the trick here is going to be to figure out what that side length is. So I'm going to introduce a new variable here. We'll call it x. And x is going to be this length right here, from the top of the pyramid to the square. And I'm just going to tell you this for the sake of time. If x is the distance from the top of this square pyramid to there, using similar triangles, I could show that this side length right here, that right there, is also going to be x. And the reason is the height of the overall pyramid is 3, and the side length of the whole big pyramid is 3. So using similar triangles, I could show that.
I forgot my
X squared. So the area is going to be x squared. So the volume of this pyramid is going to be the integral of x squared with respect to x, because x squared is the area of each cross-section. Now, the next question is, what are my limits going to be? What's the smallest the x value can be here? 0. What's the biggest the x value can be? 3. And I'm going to leave it to you to finish this. And then once you finish this integral, evaluate this integral, I want you to confirm that you get the same answer for this as you would have if you used geometry.